Good morning, ladies and gentlemen. I want to talk to you about something, although the title is called Data Without Limits, I want to talk to you about something which is called the fourth paradigm. If we think about how science evolved over the years, the first paradigm was that science was empirical. Thousands of years ago, scientists would describe the things they would see around them. Hundreds of years ago, they changed into the second paradigm, which was the theoretical one. Scientists started building models and started to describe how they thought the world should work from a theoretical point of view. And then tens of years ago, this shifted to a computational model, where we use simulation to take those models that we had and actually simulate and see whether they looked anything like the real world that we saw around us. But the fourth paradigm is radically different. The fourth paradigm means that we collect massive amounts of data about what we observe around us, and then analyze that data to see what is actually going on around us. And so the fourth paradigm is something that not only actually influences science, but it influences the way that we do business as well. And so in my talk here today, I'll go into a number of examples of how this is working around us, but also how the kind of technological side of this is actually driven by cloud computing. And cloud computing is something that gives us unlimited access to storage and to computation to do science that we would never be able to do before. So if we go back about, I think, something like 10, 15 years ago, a number of us were involved in something called the Human Genome Project. Yeah? This was a way to sequence one human genome and to actually be able to study the different characteristics that we could find in that. It took about 13 years to complete this project, was extremely expensive to do, and the resulting data set of that was actually, in today's terms, relatively small, only about 1 gigabyte. Yeah, then we moved on and we actually thought that why don't we start actually sequencing other animals? Yeah? And why don't we, then we can compare what is actually different in these animals and see whether there's actually interesting things to learn about. The resulting data sets of those were in the hundreds of gigabytes. And we needed increased computational powers to be able to actually work our way through this data. But the next generation that started sort of building about 5 years ago was that we now have these massive machinery, the sequencing engines, that are able to actually take these genomes and do the sequencing at much, much lower cost than it was able to do before. Yeah, and so this results in data sets that are in the order of terabytes. And one very specific project that is going on right now is called the 1,000 Genome Project. Imagine we would have the genomes of thousands of humans, and we could actually study the variations between humans and what are the kind of things that we can learn from that. And so this 1,000 Genome Project generates so much data, hundreds of terabytes of data, that it's not easy for any hospital or for any scientist to actually be able to afford this, or to actually be able to build sort of supercomputers around this that are capable of actually working your way through this data. So Amazon, the Amazon Web Services, the cloud division of Amazontcom, has, together with the National Institute of Health, put all of this data online and make it available for everyone to do research on. And so at this moment, we have 1,700 genomes available, and this is about 200 terabytes of data. And what is 200 terabytes of data? It's about 30,000 DVDs. That's about the size of the data that is available. And every researcher can actually approach Amazon for grants if they want to work on this data, or they can actually bring their own grants to get unlimited computational power to work the way through this data set. Actually, here in Seoul, the Genome Medicine Institute of the Seoul National University is one of those universities that is actually using these cloud computing technologies to work on their protein folding applications, to really speed up the work they do in drug research. But a really interesting example of actually this is a company in the United States called Cycle Computing. They help other companies that are interested in drug research to build massive, massive supercomputers to tremendously speed up drug research. And so their goal in life is to actually use cloud computing to start doing the science that we're capable of. Yeah? Because with the absence of these massive computational and storage engines, we were never able to do this kind of research in time frames that really make sense for humanity. So they actually built supercomputers out of these loosely coupled pieces that run in the Amazon cloud, and they built ones in the past years that run up to 30,000 cores. But something that they did at the beginning of this year is actually pretty spectacular. They built a 50,000 core supercomputer out of components that live in the cloud. And they used the Amazon cloud for this, and they actually used machinery out of the 8 different regions that we have around the world, and made all of those machines collaborate on one particular drug problem. Yeah, so why does this actually matter? Why is this massive number of machines actually important? Yeah, so if we look at the kind of area that they're targeting, there's about 12 million people per year being diagnosed with cancer. Yeah? And so for these people, every day that they're not having access to the right drugs is absolutely crucial. And you can imagine that. Yeah? And so they work together with a company called Schrödinger, who works on computational chemistry algorithms. The goal of that is to find new drugs to treat cancer. And how does this work? Yeah? So basically, if you look at all the proteins that are in a cell, you're going to look for docking points, points where you can insert in that protein a molecule to change the behavior of that protein. That's the basis of how these kind of drugs work. Yeah? In essence, it's like the protein is a lock. Yeah? And then you find the molecule that fits into that lock. The problem is that there is not just 6 keys like you would normally have in your pocket. There are millions and millions of keys that you need to try to see whether they actually fit in that lock. And so most of these systems in the past were done through what's called high-performance compute systems. And one of the principles around the high-performance compute systems is that whenever you want to use them, you always wish they were bigger. And when you're not using them and they're standing in the corner of your office, they are way too expensive to keep around. So it was the case that HPC systems were actually only available for the elite because they could really afford it. Definitely, they were never of the size that you required it. So the challenge that Cycle Compute started with in thinking about using all of these cloud resources for research was that they wanted to run a very high quality screen of millions, in this case 21 million different compounds, to see whether they would fit in any of these proteins. And this was very different from how Schrödinger used to do this. Because they didn't have enough compute resources, what they would do, their first run would always be a very coarse-grained run, quickly weeding out things that they thought had no chance whatsoever. But they knew that they were actually passing over very good opportunities. And so they wanted to do a high-quality run with the finest algorithm that they could find. And for that, they really needed this very huge amount of compute capability. And so this is actually a graph how that compute capability came online. And took 2 hours to actually bring the 50,000 cores online. And then for 1 hour, they ran these algorithms. And so in essence, what we see here is that what used to take months, if not years, to complete, actually finished in 3 hours for $5,000 per hour. Yeah, so if we look again at those numbers, we are talking here about 12.5 years of compute work done in 1 hour for $5,000. This completely, radically changes the way that drug science is being done. Suddenly, you can actually speed up drug research, cancer drug research, from going from months of work in sort of coarse-grained algorithms to hours of work at very, very fine-grained algorithms. This is extremely crucial, because remember, for all of these people, every day is crucial. So coming back to what I said earlier on, how the world of science is changing, many of these stories you will find back in a book called The Fourth Paradigm. The fourth paradigm actually was a term that was coined by the famous researcher Jim Gray, and this book has been written in his memory. And of course, working for Amazon, I have to recommend you a book. This book actually, in its Kindle form, will only cost you 99 cents. And remember, you do not need a Kindle device to actually read Kindle books. You can read it on your iPad, your phone, the web, things like that. This is the URL, the short URL, if you're interested in actually getting the book. The book is a collection of essays that are written in the memory of Jim Gray, who was regrettably lost at sea, and actually describe how science is changing over time. Now, so let's also take this into the world of business, where I like to call this science as well as business data-intensive or data-centric science. Unfortunately, or maybe fortunately, I don't know, the popular press has slammed a bit other title on top of this. It's called big data. That's what you will find back in many of the terms today. And for me, if I would have to find some definition of it that actually works for me, fortunately, it is a very vague definition for everybody, is this one works really for me. I think big data is all about the collection of large amounts of data to create a competitive advantage. Why is that actually so important today? I think because business is radically changing. There's an abundance of products in the market. There is murderous competition. There is increasing consumer choice and consumer power in that choice. Consumers decide what products to buy, no longer being actually part of a long cycle that a company forces you into. It's also decreasing brand loyalty. It is the case that you will switch from one piece of software to another piece of software, from one bank to another bank, because there's no loyalty towards those brands anymore, because customers feel increasingly disconnected from those brands. And of course, after 2008, there is for many businesses a lack of capital. So all these things together bring great uncertainty whether the products that you are developing are actually going to be successful or not. Maybe 10 years ago, when you would build products, you had some sense of whether a product was going to be successful or not. These days, uncertainty is great. And actually, if you look at most of the younger businesses today, a good definition of a young business or a startup is an organization that develops new products and services in an environment of great uncertainty. But actually, I think that definition works not only for startups, it works just as well for enterprises. And so many of the tools and techniques that younger businesses use today are also being applied in enterprises. Get a product in the hands of your customers really quickly, and then iterate on that product towards a goal that really customers want to see. That means there is great uncertainty whether those products are going to be successful or not. And if there is great uncertainty, you need very different resource models. You need to be able to acquire your resources when you need them. You need to be able to release them when you no longer need them. You need to be able to only use other core competencies in those resources. And you need to only pay for what you really use. And this may look like a technology kind of approach, but actually this works for many different areas as well. If we look, for example, at universities. When I went to university, I got a list of 20 different courses I had to take to graduate, period. Students today coming to university, they get a book with somewhere between 400 and 600 courses from which they can pick their own degree path. And that suddenly means that for the university, this has become a great nightmare in terms of resource planning. Because they no longer know on forehand where their resources have to go and how many resources are needed for which particular course. Why? Because consumers, in this case students, are in charge. They decide how their career path, how their study path is going to look like. And so in the technology world and in the business world, cloud computing gives this model. Yeah, you acquire resources where you need them, you release them where you no longer need them, you use others' core competency, you make sure that you can actually use all the power of fault tolerance and all these kind of things from your cloud providers, and you only pay for those resources that you need. So in some sense, and Amazon is a pioneer in this area, and that's actually the term we use for the Amazon Web Services, it's Amazon's cloud division. This means that compute, storage, databases, and a whole set of auxiliary services and a great ecosystem that sits on top of that will become like electricity. And we'll do that at price points that you will no longer have to think about. Because remember, when you entered this room, or whoever entered this room this morning, wasn't thinking about how much electricity these lamps are going to use and how much that's going to cost. That's because electricity is at a price point that we no longer have to think about these resources. And actually all these compute resources, these storage, databases, and things like that will all become so cheap that we can completely focus on what we are going to do with it instead of thinking about the electricity itself. A company here in Korea that is a substantial user of these cloud services is, for example, Samsung. Samsung's display division builds these smart TVs, and these smart TVs all connect back to a smart hub that lives in the cloud, in the Amazon cloud in this case, that serves the content and the third-party applications that these TVs are using. Now going back to actually the data, because that was where was the core of my talk, somewhere in the beginning of the year 2000, a number of IBM researchers starting seeing these massive changes in the way that business analytics were being done. And they called this the 3 V's, yeah? Where volume, velocity, and variety of the data that was being collected in enterprises was radically changing. And actually it was one of the cases where bigger is better. Where you started realizing that the more data you're able to collect, the finer grained the result is going to be that you can achieve. Now, one of those engines, for example, is the Amazon recommendation engine. That's all driven off data. Now, if you want to see examples of where this goes wrong, you should look in your favorite search engine for funny Amazon recommendations. And you will find all sorts of cases where this goes horribly wrong if you do not have enough data. For example, one image that I normally put up in this case is someone put Japanese steak knives on their wish list, and we then recommend to them that they buy Windows 7. Yeah? That's clearly a recommendation that has nothing to do with each other, and the only reason why that didn't work is that we didn't have enough data. And so this is one of the reasons why actually this new world of big data is very different from traditional business intelligence. Traditional business intelligence was all about that on forehand you already knew what kind of questions you wanted to ask. That drove the data model that you created, and that again then drove the kind of data that you collected. It was highly predictable. But this new world where bigger is better, you want to collect more and more and more data. Because it will actually help you get to finer grained results. But in this world then, in this world of more and more data, and also more and more compute that you need to actually analyze the data, again, there is great uncertainty. And uncertainty means that you have to use these different resource styles to actually be able to power this. Yeah, so this is one of my favorite states, is that if you think about big data, you should think about unlimited amount of big data. One thing though, and I'm a technologist, is that we have to think that this is not only about analytics. Big data is actually about a pipeline. It's a pipeline of different activities, and in each of those different activities, we need to make progress. We need to innovate to be able to help customers or companies to be able to actually use big data. And so it's a pipeline that begins with how to collect the data, how to get it into the place where you are actually going to do the analytics. How do you store this? What are the problems with storage? How big is this storage going to be? How do you organize this data? Then how do you analyze it? And of course, most importantly, how do you share the results? So let's look at this. So for example, in Collect, this is a good example of, again, out of the science space. The Ocean Observatory Initiative in the US has placed sensors in all of the oceans across the world. And then data from that flows back into the research networks, who then pump that into Amazon S3, the Amazon Simple Storage Service, where they become a repository for any scientist that wants to work on this data to be able to get access to it. And sometimes this data comes from outer space. This is the NASA Mars rover. All its data, again, is being funneled into the Amazon cloud, such that many different researchers can get access to this data. The next step is storage. And storage became obvious that this was a problem for many of the big data, whether it's companies or whether it's researchers. Actually storing these huge amounts of volumes of data requires, if you want to do this yourself, requires a lot of expertise. For example, in Seattle, there was a company called Razorfish, who was actually an analytics company. But they had to start putting their absolute best minds on storage, because storage was becoming almost the core of the business that they were in. And they realized that that was silly. Especially because it's actually to grow your storage systems at a rate that this data is being generated is actually pretty hard. Yeah, you cannot just drive to a store around the corner and pick up 1,000 new hard disks. Actually, if you remember at the end of last year, there were significant floods in Thailand that took down 2 Western digital factories. And it actually hampered the delivery of hard disks around the world for months. Actually, the expectation is that we will actually be impacted by this lack of hard disks, by the shortage of hard disks, for at least half a year, if not a year. Fortunately, in this Amazon cloud world, we have built redundant supply chains and all of these kind of things, so we were not affected by this. But if you were a company that would be depending on actually being able to acquire significant storage yourself, you're in great trouble at the moment. So the next step in this pipeline is organize. And there's many things fit into this bucket here. It is how to take different data sources and actually match them together. If you do simple clickstream analysis, how can you actually identify customers in your clickstream and actually map them back to customers in your customer database? Yeah, but there's also a whole section of work in Organize that is about how to maintain data quality. How to ensure that data that ends up into your data sets is actually the correct data that you really want to have in there. Now, especially in a world, for example, with much user-generated data, that might be a problem. How do you correct data? If you use multiple data sources, how can you make sure that 2 data items that actually talk about the same item actually are identified as such? Yeah, in a world where we see many content farms and things like that arise around the world, how can we validate that a particular article is indeed about Amazon.com, or if it's just a way to trick search engines to serve different advertisements? And then how do we go from unstructured data to structured data to be able to do better analytics on it? One of the tools that we use, at least at Amazon use, and quite a few other companies around the world as well, is to use crowdsourcing for this. Because humans are actually much better at recognizing, looking at 2 pieces of data and see whether they are the same. Or they're really good at actually looking at one of those content farms articles and see, is this really about Amazon, or is this someone that's trying to trick us? We use a system called Mechanical Turk for that. But there's also other areas in this organizational piece that are crowdsourcing. One of the things that we have a lack on in this world is actually data scientists. Although most data scientists are actually working for very large traditional corporations. So there's a company in Australia called Kaggle. And what Kaggle does is they use crowdsourcing for data scientists to build new predictive models. For example, one competition that Kaggle is running at the moment is funded by the Heritage Network. And what they do is they actually put out a competition with a very large data set of, I think it is about 50,000 individuals, their healthcare claim records completely anonymized over the past 5 years. And they ask data scientists to find a predictive model which of these people is going to end up in hospital in the coming year. And the ones who actually come up with the right model will win $3 million. And so, again, it's an example of crowdsourcing where the result of that crowdsourcing is going to be an algorithm that will greatly help healthcare identify risky individuals. Now then we get to the analytics piece, and I think the analytics piece is something that has been written about a lot, so I won't spend that much time on it, except for that this analytics piece is something that is absolutely not solved yet. Yeah, there is many different companies actually being founded at the moment. In the past year, I've seen at least 100 new young businesses being built and receiving funding to figure out how to actually do analytics in this new big data world. And not as much about the size of the data sets, but actually in this world where you do often iterative analysis, how can you match a business question to actually executing this at a lower level? The technique often used there at the lower level is called MapReduce. And it's a distributed systems framework for executing this kind of analytics. We provide something like that on top of our compute farm as well, making it easy for scientists and businesses to execute these programs like that. But still, it is just a distributed systems environment to execute these programs. It is not analytics by itself. Really thinking about how can a business user of this overall system continuously refining, asking questions, actually being executed at this lower level. That's an area there's still great research happening. And then, of course, we get to the last piece of this. Yeah, it is how do you actually take the results that you have created and actually be able to share that. Much data research or much data work in companies is often collaborative. You know, how do you get this data out to others? Often it works in cycles. You know, you take the results, you go back to the beginning, and you refine your algorithms again. Yeah, so for example, one area that we are collaborating on is on public data sets. On one hand, of course, some of these results are just purely private. They may be visualizations. They may be, they may be actually reports that go to partners. But one of the areas that we're really proud of is the area of public data sets. This is, for example, the area where the 1,000 Genome Project lives that we talked about before, but there's many other data sets there as well. And we continuously encourage researchers and scientists to bring their research there. There's a company in the UK called Mendeley who built an environment for you to manage your research papers. And they're on a path where they believe that the future of science is not just about the papers that you write, but with each paper actually also comes a data set. And so we're working hard to make sure that whenever scientists are actually delivering their papers, they at the same time make their data sets available as well. Yeah, with that, there comes the ability for everyone to do this. And so we can all then move to a world where actually data-centric work is becoming key. So remember, what I want you to walk away with is that the world of science and business is changing towards the fourth paradigm, to be a data-centric approach. And with that, you need actually a whole pipeline of tools underneath there. And much of that pipeline is made easy by cloud computing. With that, thank you for your attention.